All right, it's our last section of notes, 4-7, graphing linear functions. So you may notice we've been graphing linear equations, and now it's functions. So think back to what type of linear equation, what would the graph look like to have it not be a function? There's only one that we can't use. Which one is that? Undefined, right? X equals and then a constant. That's the only one who's not going to be in this section. We're going to just tweak things slightly though now that we can call the rest of them functions, so you will see that we're going to be using function notation. So function notation is a way to name a function that is defined by an equation. And it's f of x, so it's f with parentheses and an x. F of x equals mx plus b. Okay, so instead of the y, we've written f of x. The next definition is a family of functions. So it's a group of functions with similar characteristics. They may have the same slope, those kind of things, and we're going to be practicing those. An apparent linear function is the most basic linear function in a family of linear functions. So in general, we would call that f of x equals x. And then from there, we could multiply something or add something and so on. Okay. So now that we're done with our definitions, we're going to look at example 1. We need to practice seeing function notation because you're not really used to that. So instead of this f of x here, we are used to seeing this be a y equals 3x plus 1. And it says find the value of x so that f of x equals 10. So they're saying what if this y was 10? And you have to just work the problem backwards. So instead of f of x, we're going to write the number 10. Okay, that's all you're doing. What if the answer, the output, was 10? What would the input have to be? So we substitute 10 for f of x, and then off to the side here, I'm going to do my work since they didn't leave us any room. That wasn't very nice. So 9 equals 3x, divide by 3, x is 3. So the input would have to be 3 for the output to be 10. Okay, you're going to do the same thing now down here. Go ahead and pause the video and then come back and check your work. All right, so if the answer, the output was 24, what would the input have to be? Solving for x, it would have to be 5. And if the output was 17, what would the input have to be? X would equal 2. Okay, we're going to continue on with our notes here. So example 2 is text messages. It says, a wireless communicator provider estimates that the number of text messages, M, in millions, sent over several years can be modeled by this function. M equals 120t plus 95. And t represents the number of years since 2002, so that's kind of key there. And you're going to graph that function and then identify the domain and the range. Okay, so to do this, they give us the years since 2002. So if it's 0 years since 2002, what year is that? It is 2002. So I'm going to do my work over off to the side. So if t is 0, then we would plug it in and see what m would be. So m equals 120 times 0 plus 95. Anything times 0 is 0. 0 plus 95 is 95. Okay? If t equals 1, that would be m equals 120 times 1 plus 95, which is 120 plus 95, which gives you, in the millions, of 215. Okay? Continuing on, the rest of your values, you would get 335 and 455. You can go ahead and pause the video if you need some time to work those out. Okay, so I'm going to add them into my little table over here. 335 and 455. Okay, so now I'm going to do my best to graph those out. So I'm at 0 for years, and I go up to 95, so it's just below the 100. 1 and 215. 2 and 335, and 3, 4, 55. Okay, Now I can't go back in time, at least in this problem, so I'm just going up and to the right, and that's what my line is going to look like. It says the domain of the function is t is greater than or equal to 0. See our inputs? We can't do a negative year. So the biggest x value we can have, or t value, our input, is 0. Now look at your y values, or your outputs. In this case, it would be your m. Here's our x, here's our y. We're used to x and y, but in this one it's t and m. What was our biggest y value, or I'm sorry, what was our smallest y value that we could have? It was 95. So m could be 95, or it could be greater than 95. And that's how you're going to describe the domain and the range from now on. Okay, so you can see the checkpoint down there. It gives you a different type of equation. You're going to go ahead and write an equation for that one, and then come back and check and see how that you did there. Okay, so in this one it says use the model from example 2 to find the value of t. So here's my model when m is 1055. What would the t be? The t would be 8. Now you have to think about that. If t is 8, what does that mean? That means 8 years from 2002. It would be 8 years since 2002, and that's 2010. So there will be over 1 billion text messages in 2010. There's my word answer there. Okay, down at the bottom, our parent function for linear functions. It says the parent linear function is the most basic linear function. F of x equals x. That would have been like y equals x, but now we're in function notation, so we need f of x. If you get confused by f of x, you can always just change it to y, and then at the very end of the problem, go back and change it back to f of x. All right, so our next page, example 3 here, it says to graph these function and then compare it with f of x equals x. That's the parent function. So what we're going to do here is we're going to graph p of x equals x minus 4. So our y-intercept is at -4, and it goes up 1 over 1, up 1 over 1. So this line right here, this dotted line, is this graph. See how they wrote the equation next to it?
Mrs. Snyder?
All right, continuing on. So there it is. And now we're going to compare them. What do you notice about these two lines? They're parallel. Why are they parallel? Because they have the same what? The same slope. Look, up 1 over 1, up 1 over 1. Look at this guy. Up 1 over 1, up 1 over 1. So they are parallel lines. Also, the y-intercept of the p of x function is 4 less than the y-intercept. And we would also call this a vertical translation down. Vertical translation down. And we're going to say it goes down 4 units. So a translation means if I could pick up my line and just slide it down. Translation, another word for translation is slide. So we slide it down 4 units. So that's how you're going to be describing these compared to their parent function. Okay, so now how does q of x compare to the parent function f of x equals x? So what we're going to do here is graph it as well. Look at, it happens to be direct variation, doesn't it? Because its y-intercept is at 0, and it went down to right 1, down to right 1. So what we would say is this graph falls from left to right. We know that's true because it's a negative slope. And that the slope of the graph of f rises. The parent function rises. So that is one difference of the two. Q is negative. And that's the reason why. Okay, the slope of our q is negative. And the y-intercept of both graphs is the same. It is 0. Okay, so go ahead and read that over and make sure the words make sense as we put them in there. And then you're going to slide down and do checkpoint number 4 down here. And you're going to write a comparison of the two. Okay, so you should have done that. And my comparison is the slope of the parent function is 1, and it's half for the other line. The r of x line, it's only a half. So it's not as steep. Both graphs also go through the origin. The y-intercept for both is the origin. Okay, so we're going to just fill in this last page here. Actually, I'm going to have you do it. I want you to go through and see if you can figure out the pieces to the puzzle, what missing words go in there, and then go ahead and come back and see my answers. All right, so if I have this up here, my very first one, it's x plus b, and if you're looking here to these 3 lines, what do you notice? They have the same slope, they have different y-intercepts, and the graphs of this family are vertical translations of the original. So one slid up and one slid down. Those are vertical translations. We've slid them along the y-axis. That's a slide vertically. The next one, when m is greater than 0, so when this slope here is greater than 0, you know the slope is going to be positive. All the graphs have the same y-intercept. They're all going to cross at the origin. And these are called stretches or shrinks. And we're going to be talking about this in the future. But if it's steeper, we've shrunk it. I'm sorry, if it's steeper, we've stretched it vertically. And if it's not as steep like this guy, we've shrunk it vertically. And that's going to be kind of in your future. We're just introducing that to you right now. The last part down here, when m is less than 0, you know that it has a negative slope, okay? And the graph, they all have the same y-intercept at the origin, and the graphs of this family are also stretches or shrinks. They could also be reflections. So think about what a reflection means. If you're looking in the mirror, they have reflected. They're a different direction. And again, we're just starting to introduce you to those terms. So if you don't feel like you're 100% on this table, it's okay, because we're going to be spending lots of talking in the next few chapters about translations and stretches and shrinks and reflections. Okay, so you are on your way to do the bookwork, okay, which is the function notation bookwork.